In this tutorial, we'll review some of the basic features of exponentials and logarithms. We'll begin with exponentials. When we write 10 cubed, what we really mean is 10 times 10 times 10. In other words, 10 multiplied by itself 3 times. Likewise, when we write 10 to the 5th, we mean 10 times 10 times 10, a total of 5 times 10 times 10. So let's make a little list for ourselves. Here, for example, 10 to the first power is just 10. 10 squared would be 10 times 10, or 100. 10 cubed would be 1,000. 10 to the fourth would be 10,000, and so on. So you see how as you increase the exponent, goes from 1 to 2 to 3 to 4, the value of this function grows very, very rapidly. We can also go in the opposite direction. As we lower the exponent, when we go from exponent 4 to 3, we're dividing by 10. When we go from 3 to 2, we're dividing by 10. From 2 to 1, dividing by 10. So when we go from 1 to 0, we divide 10 by 10 to get 1. So 10 to the 0 is defined to be 1. If we then go 10 to the negative 1, we divide by 10 again. So 10 to the negative 1 is 1/10, or 0.1. 10 to the negative 2, we divide by 10 again, and we get 1 over 100, or 0.01. Likewise, 10 to the negative 3 is 1 over 1,000, or 0.001. In general, 10 to the negative power is just 1 over 10 to the positive power. So 10 to the negative 2 is 1 over 10 squared. We can see that here. Let's make a graph of 10 to the x power. So we saw by looking at these that as we increase the exponent, 10 squared, 10 cubed, 10 to the fourth, each successive number becomes a factor of 10 larger. So this function, 10 to the x, is growing extremely rapidly. So it kind of shoots up like this. That's called exponential growth. Likewise, when we start going into negative values of x, 10 to a negative number is just 1 over 10 to that positive value. So we start getting to very, very small numbers. For example, 10 to the negative 3 is 1 over 1,000. 10 to the negative 5 would be 1 over 10, 100,000. So this is what a general exponential function looks like. It grows very, very rapidly is the key point. There's one simple rule that you should remember for exponentials. Consider, for example, 10 squared times 10 cubed. Now let's think about what that means. 10 squared means 10 times 10. And then we're multiplying that by 10 cubed. And 10 cubed means 10 times 10 times 10. So you can see that this is the same thing as multiplying 10 by itself a total of 5 times. So this is the same as 10 to the 5th. Likewise, you can check that 10 to the 4th times 10 to the 18th is the same as 10 to the 22nd. Or more generally, 10 raised to some power a times 10 raised to some power b is the same as 10 raised to the a plus bth power. And this is our basic rule about combining exponentials. By the way, we don't always have to work with powers of 10. For example, the function 2 to the x is simply 2 times 2 times 2, a total of x times. So 2 to the 5th would be 2 times 2 times 2 times 2 times 2, for instance. Likewise, there's a number called e whose approximate value is 2.718. So for example, e cubed would simply be e times e times e. More generally, e to the x would be e times e times e times e, a total of x times. Next, we'll consider the notion of a logarithm, also known as log, which is basically the inverse of an exponential. Let's motivate this by reconsidering that list of exponentials that we worked with earlier. Recall that 10 to the first power is 10, 10 squared is 100, 10 cubed is 1,000, 10 to the fourth is 10,000, and so on. Let's now turn this around. Suppose I ask 10 raised to what power would give me 1,000? Well, we can see that the answer is 10 raised to the third power is 1,000. Likewise, suppose I ask 10 raised to what power would give me 1,000,000? Well, we can see that the answer is 10 raised to the sixth power would give me 1,000,000. More generally, if I say 10 raised to what power would give me some specified number x, then we call that answer, that power, we call it the log of x. Let me repeat that. You give me your favorite number x, and we want to know 10 raised to what power will give me your favorite number. And the answer is 10 raised to this power will give me the favorite number. So for example, if your favorite number is 1,000 and we ask the question 10 raised to what power will give me 1,000, then the answer is log of 1,000, which is the same thing as 3 because 10 raised to the third power gives me 1,000. Likewise, if your favorite number is 1,000,000 and we say 10 raised to what power is equal to 1,000,000, in other words, how many times do I have to multiply 10 by itself in order to get 1,000,000, we call the answer log of 1,000,000, which we can see is just must be equal to 6. So once again, if I say 10 raised to what power would give me your favorite number x, the answer is that power must equal log of x. Or in other words, 10 raised to the log of x must equal your favorite number x. It's helpful to visualize what the log of x function looks like. And here's a typical graph of y equals log of x. Now, again, always think about what it means. What does log of x mean? When you're taking the logarithm of any number, you're asking how many times do you have to multiply 10 by itself to get the specified number? For example, let's look at this plot, and let's look at when x equals 100. Okay, if I take log of 100, I'm really asking how many times do I have to multiply 10 by itself, or 10 raised to what power will give me 100? 2. So you see, a general log plot looks something like this. It's growing, but it doesn't grow very rapidly. Another way of thinking about what a log function is as the inverse of the exponential function 10 to the x. So 10 to the x and log x are inverses of one another. Let me give you an analogy. The function square root of x and x squared are also inverse functions of one another. For example, if I start with the number 5, if I square it, that gives me 25. But then if I take the square root of it, square root of 25, I get back to 5. So here I squared it, and here I took the square root. They undid one another. The action of one of the functions undid the action of the other. Let me give you another example. Suppose I take the number 5 and I take the square root of it. So here I have square root of 5. And then I square this thing, the square root of 5. That will bring me back to 5. So if I take the square root of a number and square it, it brings me back to the original number. Likewise, if I take a number and I square it, and then I take the square root, I get back to the original number. More generally, if I take a number x, I take the square root of it, and then I square it, I get back the original number. Similarly, if I take a number x, and first I square that, and then I take the square root of that, I get back the original number. Here I'm ignoring a minor issue having to do with when you take the square root of something, it can be plus or minus the value. Just ignore that. The point here is that square root of x and x squared are inverse functions of one another. Now let's get back to the main point. Log of x and 10 to the x are inverse functions of one another. So to see what that means, suppose x equals 5. If I then take the logarithm of that number, so I take the logarithm of 5, I get this. But then if I exponentiate that number, I'll get 10 raised to the log of 5 power, which is the same thing as 5. In other words, I get back the original number. Similarly, if I start with the number 5 and I exponentiate it, so that would give me 10 to the 5th. And then if I take the logarithm of 10 to the 5th, that would give me log of 10 to the 5th, which would equal 5. So logarithms and exponential functions, they undo the action of one another. They are inverses of one another. By the way, we've been defining logarithms using so-called base 10. In other words, we've been asking the question, 10 raised to what power gives me a certain number? And the answer is log of the number. For example, 10 raised to what power would give me 1,000? The answer is log of 1,000, which we've seen is equal to 3. So 10 raised to the third power would give us 1,000. But we don't always have to work with powers of 10. For example, recall that the number e is defined to be approximately equal to 2.718. And then we can ask a question, e raised to what power would give us, for example, the number 53? And the answer to that question is a logarithm, but it's not a logarithm with respect to base 10, but it's a logarithm with respect to base e. So we write it a little differently, and we express it as follows. We say that the answer is the natural logarithm, also pronounced ln, of 53. So in other words, if we took the number e and we raised it to this power, it would give us 53. By the way, the function ln of x, or the natural log of x, and the function e to the x are inverses of one another in the same way that the function log of x and the function 10 to the x are inverses to one another. Ln of x and log of x are very closely related, just like raising a number e to a certain power and raising the number 10 to a certain power. Those two functions are very similar to one another. Finally, there are 3 rules about logarithms that you should remember. The first one is that the log of the product of two numbers, a times b, is the same as the logarithm of the first number plus the logarithm of the second number. The second rule to remember is that the log of one number divided by another number, so a divided by b, is the same as the log of the first number, a, minus the log of the second number, b. And finally, the third rule to remember is that the logarithm of one number a raised to another power, b, so a to the b, is the same as b times log of a. By the way, you'll remember that the natural log function is very similar to the logarithm function. It's just that this one refers to base 10, so you're raising 10 to some power, and this refers to base e, you're raising e to some power. But they're very, very similar functions, and they have the same basic behaviors. So for example, this first property that applied to logarithms base 10, it also applies to natural logarithms. So I could write ln of a times b is the same thing as ln of a plus ln of b. And similarly for these two properties.